Just say again. Can you type for me? What is your name? Put up your hand and I can see your name. Just put up your hand. The lady that was speaking now, it's very unclear.
She just said that we can continue.
Okay. I'm continuing. Somewhere I cannot hear. A voice is very, very unclear to me. Right, so last chapter quickly. So now we finished with cables and joints and so on. And we are doing the laser. We're going to do the laser. We're going to do the basic stuff. How does a laser work? I'm going to tell you how it works. It's got a cavity. It's got a Fabry-Perot cavity, guys. It's very interesting, actually. I'll tell you how the laser works, and you must know how a laser works. Also, we've got injection lasers. Injection laser diodes. And then we talk about non-semiconductor lasers, like there's also gas lasers and so on. And so on. So I'm going to go to the first one. The three main types of optical light sources. The light source is like your laser or LED. It's a light source can be an incandescent lamp. So you can shine that down a fiber easily, not a problem. But people, just imagine how little of that light will go into the fiber. The fiber is as thin as a hair, so less than 0.1% will go. So normal incandescent lamp will not work well, but it will sort of work, but very badly. It's wideband, okay? Now, monochromatic incoherent sources is like LEDs. They can also be sources. And then also monochromatic coherent sources, which are lasers. So there are different lasers available. Remember, they are coherent. LEDs are incoherent, do you see here? So coherent means like, I wish I can explain that to you. It's a bit difficult. Okay, light comes in sine waves, okay? So when there's a sine wave and all the rays of the laser are coherent, then it means all those sine waves are in sync. All of them going up at the same time means they are in synchronization. However, incoherent light, the sine waves don't come up all the time. Let me just show you on the camera. I'll stop this thing. Can you see my page here? Can you see my page here, people? Can you see my page?
Yes.
So what you will have is the sine waves will look like that. So incoherent light for LEDs is incoherent, all right? LEDs are not very good. So incoherent light, it will start there and then it will start here. You see, and it will have a different frequency. This incoherent. And also it might be a slow one. This one is not in sync with that one, that's not in sync. This is incoherent light. There's two problems with it. The first problem, the frequencies are different, and also the peaks there are on different times. It's out of sync, you see. They're not in synchronization. So there's problems with incoherent light. This is an LED and also an incandescent lamp. These lamps, these normal old globes, these old 60 and 70 watt globes that you used to get, which is like banned now. And also LED globes. That light, the white light is very random, it's like this. However, coherent light. Coherent light is more expensive because this light is special and we're going to force it to be in sync, and we're going to force this light to have one frequency. So the modes of this light will look like this. This can be different modes, né? That mode is a ray of light. It's that color, it's that frequency. This mode is this one, it's got a different frequency, different color. This mode is like that. So they're all incoherent. The coherent light, what we have, we only want one mode. So the frequency looks like that. The next ray of light, the next mode looks like, how does it look? On top of that one. The next one on top of that one. The next one also on top of that one. This is coherent light. This light is very focused, it's very strong, it will melt your eyes. It's very powerful energy in that one light. So all of that is together. It's one beam. The light is in sync with each other. There's no different frequency. There's only one mode. There's one mode. This light had three modes. Three different. It's all scattered. It's not very strong. It's an LED. It will never burn your eyes. But a laser, you'll burn someone's retina off. Even these 100 milliwatt lasers that you buy, the children play with, it will burn the eyes. It will do a lot of damage. It will even melt metal, steel, wood, and plastic, anything. It will. I know a guy. This guy worked with a big laser printer, a laser cutter, and he wanted to adjust it. You know, you can't see the laser light, right? So what he did, he put his hand in there, and he just wanted to adjust it. And that thing cut his hand open from there to there, very deep into his skin. So very dangerous, this laser light. They are coherent, they're very strong, and they're in sync. You've got it now what's incoherent, guys. Any questions? Also, light is, let's say something else about light. If you've got glasses, there's your glasses, your sunglasses, né? And light is also polarized. They found light is vertically polarized, or it can be horizontal polarized, depending on your laser or on your light. Not only laser, normal light also. But it's 90 degrees or 0 degrees polarized. So it can either go in that plane or in that plane. So what I do, Polaroid. If you put Polaroid on in this direction, only half of this and half of that will get through. However, if you put a Polaroid on in this direction, vertical Polaroid for your eyeglasses, this is how eyeglasses Polaroids work. Vertical polarization. Then it will only allow this light in. Nothing of that light. So your light will be only 50%. But the way you turn the Polaroid, it's slotted like that, right? If you turn it like this, you see there, no light will come through. Completely dark. If you want complete darkness, they use two Polaroids and they just put it 90 degrees. There's no light coming through. Horizontal light can't get through, and vertical light also can't get through that. Right, just interesting. Any questions on that? Well, no one is talking to me. Right, no questions. It means you are not interested in this stuff I'm telling. Huh? Am I so boring? Right, guys. Next thing, I'll stop the boring stuff. Properties of injection laser and LEDs, right? You must know them. The size and configuration must be compatible with the launching light into the optical fiber. So the size must be compatible with the fiber. Okay? The light output should be highly directional. Highly directional means not in the sense of polarization of Polaroid, but sort of the light must come out in one spot or in one angle, a small angle. Right? It must accurately track the electrical input signal. So if you want a sound wave to be mixed with the laser light, for instance, it must track that sound wave very accurately, so that you don't have distortion. It should emit light at wavelengths where the fiber has low losses. Only at the wavelengths where the fiber has low losses. It doesn't help when the fiber has high losses, you use that wavelength or that frequencies. It's no good. Why will you do that? That's crazy. So you want the wavelengths where the fiber works well, where the fiber has low losses. It must be capable of simple signal modulation. They want to modulate. You can use both an LED and a laser for modulation. Okay, it will work both. Couple sufficient optical power to overcome attenuation. A LED, you're not going to get this right. It's impossible because the light goes on all directions for LEDs. Okay, the only one that will work well with this point will be a laser, which laser is one direction. Okay, and it's got sufficient optical power. Like I said, it will burn your retina inside your eyes. That's how powerful it is. Now, it should have a very narrow spectral bandwidth or a line width. Spectral bandwidth means when you make an FFT of the signals of those frequencies, it will be very narrow. Okay, so there's very little dispersion, because dispersion is a big problem for us. Point number 7, it must be capable of maintaining a stable optical output. It must not jump around. It must not jigga. Because if it's jigga, it will go less, then it's more, then it's this, then it's that. You know what's jigga. So it must be, what I'm meaning by that actually is, it must maintain a stable optical output. Right? Even if the temperature changes, it must not go less or more. It must be stable. 1 milliwatt, it must stay 1 milliwatt. It must not become 1.5 milliwatt. Right. It's essential that the source is comparatively cheap. People, they are not cheap. Lasers cost 1,000 rand or 10,000 rand. It's very expensive. But what it says here, they said it's essential that it is comparatively cheap and highly reliable. Those two are very important. So it must be cheap and reliable. That's all. That is the properties of injection lasers and LEDs. Right, that's what we need. For this, these points are the points that we need to establish a good source. These points are creating a good source for it. These are the characteristics of a good source. Okay. Whether it's a laser or an LED. I've got other points here later on where we will say what's the difference between lasers and LEDs. That's another story. The difference between these two. Right, I'm gonna skip stuff here. Luckily, this chapter is not too long. Basic concepts. They talk about laser. Laser stands for, you must know this, people. Please mark it. Laser stands for light amplification by stimulated emission radiation. So a laser is actually an amplifier. Did you know? That Fabry-Perot chamber that I talked about is actually an amplifier. It's a light amplifier, not an op-amp or a transistor or an electronic amplifier. It amplifies light. Not like a torch which got a constant light, no. A laser actually amplifies the light by hundreds of times. And it amplifies light by stimulated emission. That's how it amplifies light. So now you know what's a laser. By contrast, the LED provides incoherent gain. It's not coherent. Incoherent is these waves that are out of shape, out of sync, and out of frequency. Remember, I've given you the picture on the camera now. Right, absorption and emission radiation. You must know this formula. The energy, optical energy, equals HF. H is Planck's constant. You must know it in your head. I'm not giving it in exam. It's 6.6 126 times 10 to the minus 34 joule. It's Planck's constant, this one. You must know Planck's constant. So to get the energy of a light beam, we will take Planck's constant with multiplied by the frequency of the light. Did you know the higher the frequency goes of a light, the more energy it has? For instance, blue light. You know blue light and purple light. It's got a much higher frequency than red light. That's why when they cut steel, they don't cut it with a red light. You're going to cut steel with that laser. They put in a purple or a UV laser. It's much more energy. Right. Also, it's interesting that certain crystals changes the frequency of light. Ne? So they will use a certain frequency to actually get more energy out of a light beam. It will actually change the frequency. And changing the frequency, it will give you energy as HF. It means your energy will be higher. It's just for interest's sake. There are crystals, I forgot the crystal name, but it's in nature. You found them underground. These crystals, I've got one here at home actually. These crystals will actually change the frequency of the laser. And it will give higher energy out. People, this is just in a laser. What you'll have is three states. Normal absorption state, where the photon or light gets absorbed. Then it has spontaneous emission. Spontaneous emission is there is emission of light without a battery. You don't need a battery. If you actually look at a laser chamber, né, and there's no battery in it, it actually gives out a little bit of laser light. If you look with your eyes into it, you will find that there's actually light coming from that laser, but there's no power. They call that spontaneous emission. So in a dark night, you will actually see that light glow without power. Without your batteries can be totally flat. It's spontaneous emission. However, with lasers it works like this. The light comes in here, hits the surface of the laser, okay? And then two light beams, two photons will leave. That means it's stimulated emission. But this one, you need a battery, you need power. So the light is generated by the laser and it gets amplified times 2. Then these two light beams will hit the surface and they will split up and become 4. And this is how a laser can amplify light, this last one here. We call it stimulate emission. So a laser works, like in the name they indicated there, the laser works with stimulated emission. And that's how the amplification works, the amplification of light. Right, I'm not going detail, you don't have to know this picture. But I'm just saying what is spontaneous emission is without a battery. And this one is stimulated emission. It's when you've got a power source and it doubles the energy every time, or the light. Not really the energy, it doubles the light coming off the surface. Stimulate laser light, there's the same frequency, the same phase, and the same polarization. Remember on my camera, I showed you the Polaroid, I just showed this basically. So, it's the same frequency, same phase, and same polarization. Those three things is what makes up coherent light. Coherency is these three things together. If I ever ask you what is coherent light, now you know what's coherent light. Okay, Einstein worked from day one with light. He's the major guy that worked with light. He discovered most things about light. No one after him discovered anything new. He was the last guy. In 1917, he figured everything out about light and so on. This was 100 years ago. He showed that absorption, spontaneous, and stimulated light are related to each other. And they call it the Einstein relations formulas. He made the formulas. He did experiments actually with it. And he did the groundwork for our lasers today. It all comes from Einstein. Very interesting. So what we know today is nothing more than what he knew. He knew everything. That guy was very clever. So the Einstein coefficient is written here, and he defined these formulas. We don't have to learn it. I'm just showing you where it comes from. And how did it in there? This is the Einstein relations also. And I'm coming to this one, which Einstein also worked on. Now, people, the stimulated emission rate, right? The stimulated emission rate is equal to, okay, sorry, this formula. It's given by this formula. Stimulated emission rate over spontaneous emission rate. Well, there's an example here, and you can look through this example on your own. It's just a ratio of stimulated to spontaneous emission rate to show how efficient that material is. You don't have to know the formula, but you can go through the example. See the frequency, guys, you must know this, is related to the speed of light over lambda, which is the wavelength. Do you see here? So the frequency and lambda is indirectly proportional, completely. The speed of light you must know. It's 2998 times 10 to the 8. Okay? That, you must know that. I'm not giving you in the test, that value. Okay. The Boltzmann's constant and the speed of light you must know. And also electron volt, E. You must know that. 1.6 times what? I forgot now. But you've got to know that as well. Okay, I'm skipping stuff here. I'm coming to this important picture. You must know it, and I will ask it, and you will not know how to draw it. And you will not know how this works. This is a laser Fabry-Perot chamber. You see this block here? Is this block in real life? It's about 2 millimeter by 1 millimeter. Now the laser will amplify it inside this block here. And the stimulated emission will happen here on these mirrors on the left and right hand side. It's charged with a voltage, and these two mirrors are opposite each other in the Fabry-Perot chamber. Fabry and Perot is the guys, these guys here. They call it the Fabry-Perot resonator. So the laser light will resonate here, and through stimulation, every light beam that hits this mirror will split up in 2 light beams. And those 2 light beams hitting here will split up in 4 light beams. The 4 light beams will split up in 8 light beams. It's stimulated emission. That is an amplifier, and that is how light gets amplified without transistors, without valves, and without op-amps. You amplify the light here. It's a very special chamber. Our torches doesn't have it in, otherwise the light will be very, very bright coming from the torch. Right, so these 2 mirrors are a specific distance from each other, and it's tuned to the frequency of this laser. That L, that length, is from the left mirror to the right mirror. It's a distance from that one to that one in meters. The amplifying medium is just these 2 mirrors here and the chamber. It's sealed off, and light cannot escape here, except on the right hand side. You see here, there's a little hole, optical output. 5% of this light can escape through that hole, and this is the laser coming out of the chamber. And that is how a laser light is generated. This whole Fabry-Perot resonator will generate laser light. But most light will be reflected black in the chamber, and it will amplify more and more and more, and becoming stronger and stronger. The frequency will be the same, and the phase will be the same, and also the polarization will be the same. It's coherent light. That coherent light will then escape out of that small hole there, and that's your laser beam. When you make the hole bigger, the laser beam will be thicker and more energy will escape. If you make it much bigger, a lot of energy will escape, and it will burn through wood and steel. Okay, you can read this stuff. You must know this. You must know how the laser works. You must know that it works through stimulated emission. You must know that magic word. You must know the word Fabry Perot. If you don't mention those words, I will eat your marks here. You must know everything in yellow here below the paragraph. You must know this. And you must know that there's positive feedback. You see this. Positive feedback by reflection at the mirrors. You must know that. So please learn this picture for the test and exam. This is the frequency of a laser. This is how you calculate it. Frequency is Q. Q is an integer value that you'll be given. Alright. So it's Q times C, the speed of light, divided by 2N times L. L is the length of the chamber, the Fabry Perot chamber. Do you remember the length? The distance between the mirrors? You tune the frequency by tuning their distance. You can tune the frequency of the laser. Also here, the modes is separated by a frequency interval. So the frequency interval delta F equals speed of light over 2 L. Very simple. Or you can calculate this, the frequency separation. For that formula Q and if you can do this example 6.3, I've asked it 2 times in the papers. There are the dates. I've asked that before. In the laser, this is how the FFT looks, and this is that separation that I talked of. Remember the separation denoted by this formula. Okay, there's different modes in a laser, vertical modes, and it can have horizontal modes also, different modes. You don't have to know the picture, just note that this is some of the modes in a laser looks like that. There's a threshold condition for laser. What is the threshold making a laser work or not work? In other words, the laser shines or it's dead. There's a threshold. Now, the conditions for oscillation is when the gain in the amplifying medium balances the losses. So when the gain is exactly equal to the losses. You remember that hole where on a right-hand mirror where the laser light escapes? I just talked about now. That hole, you make it a specific size, you tune that size so that the gain in a medium is same as the losses at the beam there. So actually the beam is like 50% of the light goes through it. So that's a threshold condition for laser oscillation. You guys must know it. In addition, a minimum of threshold gain must be attained such that laser oscillations are initiated and sustained. This is to maintain the laser light. So a laser, you cannot bleed off too much of its energy. And it will not be sustainable, it will die. Right, people, this is semiconductor lasers, and we're getting to the P-in junction. It's a P-in junction, and I'm not going to go into theory, it's very complicated, the positive and the negative side, and so on and so on. I'm not going into this theory. But you must know how the basic laser work, okay? And you must know about spontaneous emission. Spontaneous emission is, here they tell you exactly, it's forward biased a P-in diode, and it leads to the recombination of carriers across the band gap. Very complicated, né? And so on. You can read here. I'm not going much into this. I'm not going into this either. And carrier combination, I'm not going deep into that either. It's a lot of theory of how the laser really works. And I'm not interested in the deep theory. I want us more to do basic calculations. Okay, here's something. People, we get a heterojunction and we get a homojunction. There's 2 types of junctions in the silicon. It's when you've got a P in silicon, alright? So, junction when they use only one crystal, but the heterojunction if they use two separate crystals for the photo emissive property here. Okay. Heterojunction is between two adjoining single crystal semiconductors. Right. So this technique is used for the fabrication of injection lasers and high radiance LEDs. These days they make very bright LEDs, and that's what they do. They use this heterojunction. Very interesting. Not really. Right, guys. The semiconductor injection laser. What? And I told you I'm going to come back to these points here. Remember the other points there on top, those 8 points. They were just what is the good properties of a good source. But this one is what is the advantages of semiconductor lasers over normal LEDs. So the injection laser diode, you see this word here, injection laser diode, ILD. The ILD has got advantages over the normal LED. What are the advantages? An ILD is a very special laser diode. Emitting diode. So the ILD has got high radiance. A normal LED doesn't have. It's very weak. Right? It's got narrow line width. Narrow line width means it's got a specific frequency. Normal LEDs have got a lot of random frequencies. It's not one frequency. That's the difference. Modulation capabilities. You can modulate an ILD, but okay, you can also modulate an LED, I must say. You can modulate both of them. But this modulation of an ILD, the injection laser, this modulation of ILD can extend up to gigahertz. You see this frequency, gigahertz range. An LED, you can only modulate it to a few megahertz. Then it's done, it's finished, it's fairly. It can't do it. While the injection laser can do it at high frequencies and gigahertz. It's got a relative temporal coherence. So, normal LEDs doesn't have coherent light. I told you already that they have got scattered light and they are not in sync and they don't have the same phase. But an ILD is coherent light. So the light is in phase, the light is in the same plane, and also the light is that coherent light's got the same frequency. So remember those things. And the good spatial coherence, which also allows it to be focused in a lens onto one spot. So spatial coherence is not the same as temporal coherence. It allows, spatial coherence allows it to be shined on a lens onto a certain spot to give it a focused emission. So these 5 points is where ILDs is much better than LEDs. You must know these 5 things. That's why I'm hammering so much on it. I say you must know this, but don't worry. It just shows you another Fabry-Perot cavity here, and it's just the same as the above, except there's 2 laser beams coming from this one. One left and one at the right. Okay? Well, you don't have to know this picture, just skip it. You can look at it, you can... Okay, now I'm coming to something here. The efficiency of the or the quantum efficiency is the total number of output photons over the number of injected electrons, not photons. So it's how many photons you get out for this current. If you have 1 milliampere, you get 100 photons on, it's 100 to 1. It's sort of like that. Okay, my units is not right. So it's also equal to the The quantum efficiency is also equal to PE over IEG. Now PE is the power emitted there, and I is the injection current. You see there, I is the injection current, that I. Where is EG? They don't say here. EG, oh here it is, for high injection current. They don't state what EG is. But okay, forget that. Look at this formula, 6.41, you must know this one. The efficiency of emitted power of an LED. So it's a normal LED or a laser LED. So there's an efficiency of emitted power. It's the emitted power over the battery power. This is what your power source is. So remember, this is battery power. Now power equals voltage times current, or I square R. That's the emitted power in optical power, but this is the battery power of the power supply. And that gives you the efficiency. You see, that's formula for that. Any questions on that? Also, the efficiency of emitted power equals the efficiency, ET was a formula here, wait, yeah, NT is this one. You can give this formula also, formula 642. Just works to this example. This example is an example of the emitted power. So works to this example, and know how this example works as well. You must know it. Then you must know this one. This is a stripe DH laser. You see, stripe DH laser. The stripe DH laser is a laser diode. It's got a Fabry-Perot chamber there in the middle, and here there's not a dot where the light comes on. It's a line of output. It's a white line, and it's got a bit of an angle here, and it goes. The light goes out that side as well as here. This is called a broad area DH injection laser. 1 mark for light output, 1 mark for cleave. The sides P gallium arsenic, negative gallium arsenic here. Positive gallium arsenic, negative gallium arsenic. The contact is on the top, the metallic contact for the battery, and on the bottom. 1 mark for that also. So here is a nice 6 mark question. You must know this picture. Figure 6.20. This one is another one to know. This is the same one, but in this case, it's an oxide stripe DH injection laser. So if I ask you to draw the normal DH injection laser, a broad area one, broad area DH injection, you draw that picture. If it's a oxide stripe DH injection laser, you draw this one. The difference is in that one and this one, the material is the same. This is the same, except here it's narrower. So the light comes in a narrow beam, and this beam is 45 degrees in that way. 45 is there way, so it's 90 degree by 18 degree, 9 plus 9. It's a very narrow beam, and the laser light comes on. This is the light that they use for all the injection layers today. All the injection lasers use this one. There's no light coming out there like this one. This one has got 2 beams of light, you see, and they're very scattered here. It's not a very good one. However, this one has only got one gap, and it's got a stripe here. Do you see the stripe here? This stripe makes it possible for this thing to be only 9 degrees wide here, this stripe. That one doesn't have a stripe. Do you see where's the stripe for this one? There's no stripe, so this light is very wide. This one has got a stripe contact. And your positive plate is on top here. Your negative terminal is on the bottom. Remember that. Positive contact, negative contact. For your power, you need power here. Maybe you need 5 volts on this thing. So you put the power on top and bottom. It's like a little service mount component. But remember the plume coming out here of light, it's 9 degree by 45 degree. Or 18 degree by 90 degree. So this oxide stripe injection layer is with a stripe in. See, oxide stripe and the stripes on top there. Right, please know that one as well. Okay. The laser, when you look at the FFT, it will only have a single mode, a single ray of light, a single color. So one single longitudinal mode comes out of the laser. That's how it looks. Then there's a lot of other lasers which I'm not going into. I just want to tell you, this is a non-linearity or a kink in the signal of a laser. It happens with lasers that as you increase the current, along this path from left to right. And the light output here will change with current. So when you make the current more, the light output will become more milliwatts. However, there's a non-linearity in all the lasers, and there's a kink. Don't let it catch you, because if you do work on lasers, you're going to experience this problem one day. So when you increase the current here, it actually decreases in light there at that region. And only afterwards it will increase again. So don't use this laser in this region. In this current, 200 milliamp is taboo for this laser. If you use it, you will just have trouble. So don't do that. When you work with this laser, rather work 100 milliamp to 180 milliamp in this region, which is from bottom to top there to there. Okay? Or you can work 250 milliamp to 400 milliamp. You can work with that current. Okay? Which will be from here to there. Or from here to there for the laser. Sorry, 250 to 300 milliamp. So the current determines, and in this kink or non-linearity can sit anywhere on the graph. Each laser is different, and you must look in a data sheet where it sits, and you must find out. Don't just accept that the laser is correct. It's not fine. They all have this problem. So be warned that there exist such non-linearities in lasers. Image guided lasers, I'm not going into that. And we are almost done for today. The stability figure, it's got these lasers, it's got a grating, you see there, it's got a grating, and it's got a Bragg reflection, and you can adjust it a little bit. I'm not going into this distributed feedback lasers. It's a complicated thing, and it does complicated things like this, and there's some problems between a Fabry Perot and a DFB lasers. I'm not going into that. We don't need that info here. This is the distributed Bragg effect and how it works. I'm just telling you that it is a distributed feedback laser, and it does use this Bragg effect. You don't have to learn it. You don't have to know this picture. I'm skipping. I'm just giving you background information. This is a vertical cavity surface emitting laser. In this case, guys, your contact is on top of the metal plate in the bottom. Again, you see there, bottom contact, in top contact. But the hole for the laser lights on top there. So you must be careful how you solder. Your solder pad will be around there, so that you don't damage this hole. And then inside here, you see there is a Fabry Perot chamber here with a mirror there. Also, the mirror is also in there, just like a normal laser, but it's vertical. The light will always come to the top of it. What I'm showing you is just that it exists. You don't have to know this picture. You don't have to. You can just read the background information. Injection laser characteristics. What's good about the injection laser? People, the temperature dependence of the threshold current density. So there is a temperature dependence on the current. So if the current goes from 100 milliamp to 200 milliampere, the temperature in the laser will increase a lot. Now, when the temperature increases, the current will increase again. So it causes an unstable working point. And we don't want that. That is why the lasers at this current will become so hot. At this current, so hot. At this current, it will become 60 degrees. And this different temperatures gives different currents, which gives a lot of problems with lasers, and not everyone can understand and work with a laser diode. It's very difficult because you must watch the temperature, you must measure it as well, and you must have a temperature controlled fan to fix this current to 200 milliampere. You must control the temperature to be exactly 40 degrees in this case, or 50 degrees there at this current here. So you better do temperature control on this thing. So you need a complicated electronic circuit to be able to work with this laser. But for electronic engineers studying at TUT, this is not a problem because they did electronics 4. I know they do it, but they will easily do this one. Easily. They can show me how to do it. Now, isn't it? Guys, who took electronics 4? Nobody. People, are you still there?
Yes, we're still here.
Yes, here.
Oh, thank you, thank you. I'm not talking to a ghost or something. I just want to find out if you're still there. All right. I'm almost done with the chapter. Guys, 5 minutes, I promise you. 12 o'clock, we'll be finished. Look, frequency chip. I asked this thing, what is the chip? What is that other one that we just did now? That incoherency, and what is a frequency chip? A frequency chip is when, now I must always read all this stuff, but the frequency chip is when a frequency jump from one frequency to another one. So it's producing a regulation in the device output, resulting in a phase shift of the optical field. So there is a phase shift, and this phase shift is like a line with broadening in the frequency, right? And they call it chirping. You see now, this is where that word comes out. So chirping is when there's a line with broadening. Will you remember that? That's one of my favorite questions. What is chirping? Laser chirping. And you will not know what it is. But it's basically due to some effects. You can read this paragraph. And basically it is line with broadening inside the Fabry Perot, this thing, cavity. You see there. I'll see if there's a picture here or what now. Alright, then there's noise that you must know. People, for lasers, there are noises as well. Almost said 2 types of noises. There's phase or frequency noise, okay, and also this chirping that I'm talking about is also a noise, so regarded as noise. This noise is frequency noise in the phase and the frequency, and also instability in operations such as kinks. Remember that kinks that I said? The kink in that line, it went up like this with current, a little bit down and then up again. That kink also causes noise. So people, whenever you work with a laser, beware of this one. It will bite you because it is really there. Okay. Also, there's reflection back into the device. I told you that the Fresnel lens on the fiber don't allow all of the light. Some of that light bounces off and comes back into the laser, and then it makes the laser not working. I almost said, scorro. The mode partition noise is also a problem of noise. So these four things, people, is noise in a laser. The phase of frequency noise, the instability, such as the kink against current, that kink against current, that one, and then reflection of light back into the device and mode partition noise. What will reflection light into the device do? What will this do? So external light will come into a laser. It will bugger it up because it will change its frequency. It will make it the light smaller. It can even blow the laser. So this noise is a big problem. I'm done with this. I'm done with this. I'm done with. Ah, no, man, there's another one. I thought I'm done with this chapter now. Mode hopping, there's another one. Lasers also have, it's not noise, but they call this mode hopping. A mode is basically a frequency, all right? So this frequency here will go, when you increase the power, it will go and it will go sit there. So it will go a little bit right. It will go from here, it will jump to that point. We don't want that because it will happen in the fiber and the light will not know what to do with it. So it's the receiver diode. The receiver diode at the end of the fiber will not know what to do with this. So it will, the mode frequency will jump from here to there. So mode hopping is when the laser light jumps from one frequency to another. And that's usually when it becomes hot. When your laser becomes warmer, it does this. It does mode hopping. We don't want it. How can we stop it? Yeah, I said we can stop it by putting a proper heat sink on and a cooling fan. You keep the laser cool, then this won't happen. But if you don't have a heat sink, you don't control the heat, this will happen with you. Alright, mode hopping. Remember, you must know this one. I've asked it in that question paper. Look, I'm not saying, however, if I was in 2018, 19 and 20, I don't give all my secrets away, guys. Do you think I'm crazy? So I'm just saying the one, but it's not to say it was in 2020's paper. I think it was, ne? Some people will remember this question. What is mode hopping? You can read here what it is. I can't read all the stuff for you, guys. This is really a lot of stuff. I'm going to skip this. I'm not going to do that. I'm not going to. I'm just going to tell you there are non-semiconductor lasers as well. Ne? We got CO2 lasers as well as jack lasers. All right. So they are not silicon lasers. They work with gas and so on, and it's a total different thing. I'm not doing it. You don't have to really learn them. It's just a schematic of a jack laser. CO2 lasers are used by the doctors a lot in operations and so on. But they use CO2 lasers in optical field as well. I'm skipping now. I think I'm going for the end of the chapter now. Yeah, I'm skipping heavy now. Yes, we are done for today. People, there's some problems. You don't have to give it to me. You can do this on your own. 6.3. There's another paper question. I've asked you in those two papers. You see there. I like this one for some reason. 6.5, 6.6. I've marked some problems here. Okay. Just check them out. And then I'm done for chapter 6. And then I just want to show you what we'll do in 2 weeks' time. We'll do light emitting diodes. So after lasers, chapter 7 is LEDs. And LEDs look very similar to lasers, and we'll get to that chapter 7 next time. So I'm going to stop here, people. I'm going to stop right here. Can I stop the recording? People, are there any questions? Again, I'm asking you all the time. Are there any questions about this? About lasers? Yes. Mogatswana, please talk to us.
So I just wanted to find out about the class test.
The class test. Look, we can do a class test over the... What I can do, we can do it over Brightspace, okay? If you sit at home and we do it, how's that? Do you want to do that?
Yes.
Okay, I'm not sure. Ayanda, you must come up with a day. When can we do it? So one of the evenings after work, ne? Come up with a time, tell Ayanda. She will tell me what time. Is that fine with you? We can do it in this week sometime.
Okay, sir.
Maybe Thursday evening or Friday evening or Wednesday evening. Then you come back to me, we write the class test one of the evenings online. I'll just put it on Brightspace and make sure there's no load shedding. Then we can do the test. If there's load shedding, it's a big problem for us because some people have load shedding. But I think next week will be all right, like this week. We didn't have any load shedding. Did you have load shedding this week? Last week?
No.
So hopefully no load shedding, we can write the test. You can let the others know. Is Ayanda there? Ayanda, why are you not talking to me? I can't hear you.
Can you hear me now?
Yes, I can hear you. Did you hear what I'm saying?
Yes.
Yeah, make a time and then we write the test, a 1 hour class test or so. Okay, in a week, next week.
All right.
And then also the semester test, guys. I mean, maybe in 2 weeks' time we can go to TUT. Do you want to go to TUT and write it? Let's sort it out now. Saturday in 2 weeks' time, we go to TUT, we write the semester test one. Can we do? Please tell me. Please vote. Let me just stop this recording.
Is there an option of us writing online, sir?
No, you can't. Then you can fail because remember, there's no. If you write online, then there's no. How can I say? Validation. You understand? Okay, anyone else, people? We can't write the semester. We can do the class test online, but not the semester. I think, we're not going to have an exam. I think so. In that case, the semester test is your exam, all right? You hear that?
Yes. Sir, since we do not have the exams, can't we write the class test on the next class on the 6th of November?
The test.
Yes.
Don't you want to write the semester test?
Okay.
How do you feel? Tell me your feelings. I don't know how you feel. You're not telling me.
The thing is, I'm not sure. Maybe the others have classes next week. So we can't write a class test during the week while maybe they have to study for something else.
All right, can we, in 2 weeks' time, Saturday, is that all right?
Okay. And then are we?
But is that
are we,
not the time we're supposed to write the semester test?
Explain, say that again.
In 2 weeks' time, is it not the time we're supposed to write the what's the semester test?
Yeah, we can write a semester test on the 6th of October. But the class test, one of the evenings next week. How's that? Can we do?
Say, okay, is it possible that the class test you can maybe let's say upload it on a certain day, even if it's during the week, maybe after hours, then it's available maybe until 12 o'clock. But when you go in, maybe you give us what's this time that we need to write it maybe for an hour. Then once you start writing it after an hour, it closes. How about that?
Yeah, we can do like that. So I'll do it next week, and then I will go up to 12 o'clock, and you can write any time. How's that? Are you happy now?
Happy.
Okay, that's your class test. It's very nice that we can do this. We write the class test, but the semester test, we are going to TUT in 2 weeks' time on the 6th of November. 6th November, Saturday morning, we write the semester test. Okay. Sorry, on the first 6 chapters. And by that time, guys, in 2 weeks' time, you must sort of start doing your simulations on Proteus that we can. And then for the Proteus simulations, you must come in on a Saturday and show me your simulations. I want to see it. So we'll do it there one by one. Okay, is that fine?
Just to check, sir, do you have a link for downloading it for people who don't have it on their laptops? Because I remember the previous semester you gave us a link, but it needed some login details, wara wara wara. So I lost those ones. I was gonna share with everyone.
Yeah. I don't know what happened there, but couldn't you get the link or what? Are you talking for the simulator?
Yes.
Couldn't you get the simulator, Ayanda? What happened?
What I'm saying is, do you have the link for downloading it for people who don't have it so that we can share? I still have the link, but I lost the logging. I think it's logging details. There's some logging details that you gave us the previous semester
I don't
for
have
that simulator.
I don't have it. I don't know how to get it. Actually, I don't work with it. But I know students can get access to the program and simulate with it. That's what I do know. But I don't have that information. I will see what I can find out. But what is your link for it? Can't you log into it? Can you try again to log into it and see if you can simulate?
I do have it because I've already downloaded it and installed it. It's on my PC. I'm just saying for other people who don't have it.
Oh, well, I must find out because that link was on my tutor. Remember, it was on my tutor. We work
Yeah,
not right
that's
space.
the thing.
And that's
Yeah.
I don't have my tutor anymore. They've disabled it and it's not working now anymore. So my tutor doesn't work and that information is lost now. So I don't have it on Brightspace. That's what I'm trying to tell you. But I'll find out if I can find out where the link is. But you don't have your link anymore.
The link, I do have it because I tried also installing it on my other PC. Then when I open it, it needs those details and I don't remember them.
All right, I will see if I can find that information. The login details, okay.